Dear children, let us recall our previous class topics. In previous class we had discussed force, balanced force, Newton's second law of motion, inertia, types of inertia, momentum, second law of motion, mathematical formulation of second law of motion. I hope you are all understood the topics. Today we are going to study the following topics: Newton's third law of motion, examples of third law of motion, law of conservation of momentum, mathematical formulation of conservation of momentum. Newton's third law of motion. Third law states that for every action there is an equal and opposite reaction. Newton's third law of motion is the relation between the forces themselves. Here, if one body exerts a force on another body, the other body also exerts a force on first body. All these forces are equal in magnitude but opposite in direction. Activity. Let us take two spring balances, connect them in between, fix the other end of the spring balance to a rigid support. Pull the free end of the spring balance A that both the balance shows the same reading. This phenomenon observed reveals that forces exerted by the balance A on balance B is equal and opposite in the direction to that exerted balance B on A. The force exerted by balance A on balance B is called action, while the force balance B on balance A is reaction. Other examples. Let us consider an example. If you hit the wall first, even the wall hit yours first with the same force. This force can be felt as pain. If a porter lifts a heavy load on his head, load presses the head downward and head pushes the load upward direction. These forces are equal in magnitude. Here, F1 force applied by the load on the head. F2 is force applied by the head on the load. Let us watch some more examples explaining actions-reactions pair in Newton's third law of motion.
When the birds fly, their wings push the air downwards, which is considered as action. In turn, air pushes the wings upwards in opposite direction, the reaction. Both the forces are equal in magnitude and opposite in direction. When the fish swims in water, fish push the water back and water pushes the fish in opposite direction. Both the forces are equal in magnitude but opposite in direction. Activity. Balloon rocket. Take a balloon and inflate it. Place it on a straw and thread arrangement and tape the balloon. Ask your friends to hold the thread on either side of the straw. Fix the balloon to the straw with a sticker tape. Release the air from inflated balloon by holding its neck part. We can observe that air escapes out of the balloon, but it does not move from the place. But let us perform an activity when the balloon is free. Inflate the balloon and tie its neck. Balloon is tight as air inside it exerts force on the walls of the balloon equally in all directions. When the neck is released by removing the thread, air escapes in one direction, but balloon moves in opposite direction. That is, while escaping, air exerts net force in the opposite direction, causing acceleration in the balloon.
Law of conservation of momentum. The law states that if no external force is acting on a system, the total linear momentum will remain constant. Before collision is equal to after collision. Definition of the law. When two bodies act upon one another, their total momentum remains constant. The principle of conservation of momentum is in accord with Newton's third law of motion. Momentum is never created nor destroyed. Here is an interesting activity with Newton's cradle. All the balls of the Newton's cradle have the same mass. If we have one ball of the Newton's cradle with a certain velocity before the collision, then we must have one ball with the same velocity after the collision. Let us see. This is the cradle. Here one ball has a velocity, same mass at the same velocity before and after the collision. What if two balls collide? What will happen if use three balls? We can see three balls get the final velocity. You must trust physics. Yes, finally here three balls get velocity. Of course, three balls go out. What if we use four balls? What if we drop one ball from each side? It is also conserved. What about one from one side and two from the another? Yes, here also we can see the momentum is conserved. What about two from each side? Here also we can see the momentum is conserved. 3 from one side and 2 from the other. Yes. Here also we can see it is conserved. 4 from one side, 1 from the other. Mathematical proof of law of conservation of momentum. Consider two marbles A and B. Here I am drawing the two marbles. Consider two marbles. This marble name A and B. Two marble A and it has the masses M1 and M2. Okay, then these two marbles rolling towards each other with the velocities u1 and u2, rolling towards each other. These two marbles rolling towards each other. Thus M1 has u1 velocity and M2 has u2 velocity. With the initial velocity u1 and u2 respectively, such that no other forces acting on them. Now consider that these marbles collide with each other. After some time, it is collide with each other. Collide with each other. Here, at a time t with each other, sum that time of collision for that t seconds. Then here we can write u1 and u2. u1 and u2. Then after that collision, here colliding, no, this after this collision, what happened? It gets final velocity. Both of the balls move opposite direction. After the collision, both of the balls moves opposite direction. With the final velocity, the ball A has V1 and here the final velocity ball B has what? V2. Okay, I think you are all understand the thing. Here two marbles of same mass M1 and M2 and the marbles are A and B. After it is moving towards each other with the initial velocity U1 and U2. After some time it is collide to each other. After the collision it gets the final velocity, that is V1 and V2. So from this we have to prove here the momentum is conserved. Here we can see initial momentum. Before collision there is an initial momentum. After collision there is a final momentum. We have to prove that there is the momentum is conserved. We already discussed momentum is conserved. It will neither be created nor be destroyed. So it is conserved. Before collision, what amount of the momentum it consists of, that is conserved to after momentum, that we want to prove. Then here first change in momentum of marble A in time t second. First we want to write change in momentum of marble A. Change in momentum of marble A is in time t second. That is what? Final momentum. This is final momentum. After collision, the marble A has final momentum. Before collision, it has initial momentum. Final momentum minus M1 V1 minus M1 U1. It can be right M1 into V1 minus U1. Okay. Then after that, the rate of change of momentum of marble A. Want to write the rate of change of momentum of marble A. That is what? Want to put T also. Then M1 V1 minus U1 divided by T. Then we got the rate of change of momentum of marble A. Then as the rate of change of momentum of marble A is the force exerted by the marble B on the marble A. Okay, so we can, this is exerted by a force A on B and B on A. Here now we are taking marble A, so we can take it as force 1. That is F1 is equal to force exerted on the marble A, force exerted by the marble A is equal to F1. Action force, that's the force exerted. So can take as F1. So we can write F1 is equal to M1 into V1 minus U1 divided by T. Okay, equation number 1. This is equation number 1. This is about marble A. Similarly, we can write the change in momentum of marble B in time t second. Okay, now we had written the change in momentum of marble A and rate of change of momentum we can write with the T. Then force exerted by the marble A is taken as F1. So we can take force exerted by the marble B on A, we can take as F2. Okay, so because of that, here taken as F1. F1 is equal to M1 into V1 minus U1 divided by T. Then change in momentum of marble B. Change in momentum of marble B. Okay. Then it can be write how change in momentum is what? M2V2 minus M1U. M2U2 change in momentum. Then what is rate of change of momentum? Rate of change of momentum is equal to M2 into V2 minus U2 divided by T. Okay, like this. Then after that, what we want to write? Force exerted on the marble B. Force exerted on the marble B. Force exerted on the marble B. That is taken as F2. What is that? F2. So we can write F2 is equal to what? M2 V2 minus U2 divided by T. Okay, this is equation number 2. What? First, we found the force exerted by marble A, and second, force exerted on the marble B, we can take as F2. Okay. These two equations we got. What F1 is M1 V1 minus U1 divided by T, equation number 1. F2 is M2 V2 minus U2 divided by T. Okay. Then after that, we are applying Newton's third law of motion. According to Newton's third law of motion, for every action there is an equal and opposite reaction. There is a relation, that is action reaction, there is a force, no? So there is every action there is an equal and opposite reaction. Okay, here also action reaction there, two bodies are there, so we can take as action taken as F1 and reaction taken as F2. So we can apply these two here. Then F1 is equal to minus F2. It's very important. Listen, as per Newton's third law, every action there is an equal and opposite reaction. Here is plus and here is minus. So if we are after that, it is we are applying to this relation here. In the case of marbles, F1 is the action and F2 is the reaction. So we can write like this. Then substitute the values to this equation. That is, F1 is what? M1 into V1 minus U1 divided by T is equal to, what is F2? Minus there, minus, put minus M2 V2 minus U2 divided by T. Okay, then here T will be cancelled. Then we can write M1 V1 minus U1 is equal to minus M2 V2 minus U2. Then multiply here M1 to inside of that bracket, that is we will get M1 V1 minus M1 U1 is equal to minus M2 V2 minus into minus plus M2 U2. Okay. Then here we have to rearrange initial momentum in one side and the final momentum in another side. So finally we will get m1 v1, then final momentum I am writing the left side. This minus m2 v2 come to this side. What happened? Plus m2 v2, then equal to what? m1 u1 minus m1 u1 come to this side, no, right side. That time plus my m1 v1, m1 u1 plus m2 u2. So we can rearrange this. m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. From this we can understand that this is the proof. That is, the total momentum before collision, the total momentum m1 u1 plus m2 u2, total momentum before collision is equal to total momentum after collision, that is m1 v1 plus m2 v2. Now m1 u1 plus m2 u2 is the total momentum before collision, whereas m1 v1 plus m2 v2 is the total momentum after collision. Therefore, we can say that the sum total of momentum does not change or is conserved. This is exactly what the law of conservation of momentum states.